All right, good morning. My name is Thomas Graf. I'm the co-founder and CTO of Covalent. That's the company behind Cilium, the Cilium project. I'm here to talk about how you can connect multiple Kubernetes clusters together across cloud providers. Who am I? I've been a kernel developer for a long time, spent about 10 years at Red Hat, mostly focusing on networking, security, and BPF. So I've been living low level in the kernel for a long while, and then started the Cilium project and founded a company about 1.5 years ago to drive Cilium forward. The goal of this session is to run services across cloud providers. Specifically, what we will do is we will set up a Kubernetes cluster in GCP, we'll deploy services, we'll set up a second cluster in EKS, we'll deploy the same service, and we will establish service load balancing between the cloud providers, between the clusters. And we will discuss and show how you can set up encryption between the clusters. So that's the goal of the session. And one potential use case, we'll talk about others, is that if a backend in one of the clusters fails and the zombies are coming in, it automatically load balances and uses the backend of the other cluster. So that's the HA use case. That's one. We'll discuss others. So that's the goal of the session. If you're not interested in this, you can leave the room again. What tools do we need? We need Kubernetes, of course. I think everybody is familiar, I hope, with Kubernetes. We'll repeat a little bit about the basics that we need. We will need infrastructure APIs, and I'm trying to be as generic as possible. We need some form of VPC with routing, virtual network concepts. All cloud providers support this. Your on-prem infrastructure supports this. And we need an IPsec-compatible VPN solution. All cloud providers call this VPN gateway, VPN tunnel of some sort. And typically, all cloud providers support IQE1. Some support IQE2. So that's what we need from an infrastructure perspective. If your cloud provider, if your on-prem infrastructure provides this, you can use the solution, you can set this up. The last piece we need is Cilium. What is Cilium? Cilium is an open source project, Apache licensed. It's a little bit over 2 years old. It's based on BPF, a new exciting technology which we'll talk about just a little bit. The next slide. We provide several things. First of all, we are a CNI plugin. We provide networking. We provide connectivity between pods. We implement Kubernetes services. So we're replacing kubeproxy. We're 95% there to completely rip out kubeproxy. BPF is an alternative, a better alternative for IP tables, which is the default implementation of kubeproxy. We're using the power of BPF, for example, to do multi-cluster routing. We also provide network security. So ability to define what pods, what services can talk to each other. We use an identity-based mechanism to do so. We are DNS aware, so we don't only allow you to define what pods can talk to each other, we also allow you to define what DNS requests a pod can make. We allow you to specify policy that a pod can talk to this DNS name, and Cilium will automatically track the IPs returned by the DNS server, and then the pod can only talk to that specific IP address, which allows to, in simple terms, establish policy egress to services that are running outside of the cluster. We are API and data protocol aware. That's where Envoy is coming in. We'll talk a little bit about that as well. So we not only understand services talking to each other, we also understand the HTTP REST API calls that the pods are making. We understand Kafka, Cassandra, Memcached. So you can define security policies to not only allow services to talk to each other, but for example, to say, this pod can talk to my Cassandra, but it can only do a select on that table, and everything else will be denied. So we allow you to do API-aware security. In 1.4, we will also establish transparent encryption. So you can basically turn this on, and all pod-to-pod communication inside your cluster will be encrypted. In a further release, we'll actually allow using this technology and integrate this with Istio and Envoy to enforce MTLS using kernel acceleration. The last piece, we have Envoy and Istio integration. We do sidecar acceleration, so as you deploy something like Istio, we can accelerate the communication between your pod, your applications, and the sidecar proxy. And we have a very exciting new feature coming up, which is called transparent SSL visibility. We can actually provide Envoy and Istio with visibility into data, even if your application is using SSL encryption. We will not have enough time to discuss all of this. I will focus on the multi-cluster, but I think a lot of people have heard about Cilium for the first time, so I wanted to give a quick overview. What is BPF? That's the official, semi-official logo. BPF, highly efficient sandboxed virtual machine in the Linux kernel. That's the academic version. What it really means is it's making the Linux kernel programmable at native execution speed. And that's really, really, really powerful. This is driving a lot of stuff that's happening inside of the Linux kernel right now. The technology is jointly maintained by an engineer from us and an engineer from Facebook, and then we have many collaborators across the board. We'll talk a bit about that. Who is using BPF right now? You will see, or better view will be if I show you the list of contributors, but I think a very prominent one is Facebook. Facebook has just presented their latest developments in how they leverage BPF, and they've actually been using BPF for all production traffic, publicly exposed on the internet. So every packet that went into a Facebook data center in the last 1.5 years went through a BPF program. There are many, many other use cases. Facebook is using this, Google is using this for traffic optimization QoS. They just started on implementing network security. Red Hat has upstream developers working on using BPF to replace IP tables. I think many of you may have heard about Brandon Gregg talk BPF on profiling and tracing. If not, go check it out. It's fantastic, cool stuff. There's a large investment into BPF, into this new kernel technology. Who contributes to BPF? You can see a lot of companies here. A total of 190 contributors have contributed to the kernel portion of BPF over the last 2 years. That's an intro on like Cilium and BPF, gives you a background on like where we come. So now we're going to talk and dive into how we can use BPF and Cilium to connect multiple Kubernetes clusters together. I want to level set a bit. We'll go over this quickly, but I want to make sure that we all have the same understanding. Difference between deployments and pods. Deployments is your desired state, right? You will, if you have 2 services running, you will have a deployment for the front end and a deployment for the back end. Pods are a collection or group of containers. As you scale deployments, as you define how many replicas you want of a particular deployment, that number of pods will be scheduled, right? So pods is what's being used when you scale your deployments. If you do kube control get deployment, you will see the desired state, the currently running pods, and so on. Deployments and pods. So as you deploy these pods, every pod will get a unique IP address, and they're just living on your Kubernetes cluster. So you have, let's say, 3 front ends and you have 4 back ends. How does the front end talk to the back end? Does it need to know about the specific pod IP of the back end? No, this is where the service is coming in, a Kubernetes service. So you define a Kubernetes service. It will get a so-called cluster IP or a service IP, and as the front end talks to this IP address, Kubernetes will automatically load balance to a healthy backend to a healthy pod. If you do a DNS lookup, kubedns will respond with the cluster IP. There's some special cases that I'm ignoring here, headless services, and so on. In simple terms, this is how Kubernetes services work. Relatively simple and straightforward. How does Kubernetes know whether a pod, a backend, is actually still healthy, whether it's still alive? Kubernetes allows us to define a liveness probe, and Kubernetes then will probe that backend pod every n seconds, ask, are you still alive? Are you still alive? Are you still alive? Are you still alive? And if not, it will remove it from the list of pods that the service load balances to. And this is being represented as the so-called endpoints. So as you define a Kubernetes service, Kubernetes, the API server, Kubernetes will automatically also create a endpoints. And the endpoints resource or object will contain the pod IPs of the healthy backends, of the healthy pods. This is all you need to know about Kubernetes in terms of multi-cluster. We're not introducing anything on top. We're using this exact construct to do multi-cluster. If you're an advanced user, you can manually maintain endpoints and put arbitrary IP addresses in this, and kubeproxy and other solutions will automatically load balance to those IPs as well. So this construct is not necessarily limited to pods. So what we're introducing is global services. It's a standard Kubernetes service with one addition, an annotation where we mark a service as global. As we mark this, for those that don't know, an annotation is a way that allows Kubernetes for third-party plugins or users to define or add annotations to a standardized object, and plugins or users can then interpret that annotation and do something with it. So we can annotate a standard object. So with this annotation, we're marking the backend service as global, and Cilium sees this and automatically does load balancing across clusters. Sounds good. Let's do a demo. And I really hope that the Wi-Fi is working because I will need a connection to my cloud provider. So I like to do like theme-based demos. Some of whoever I've seen a demo of me before, it's a new demo. It looks similar, but it's going to be a new demo. A long time ago, in a container cluster far, far away, it is a period of civil war. The empire has adopted Kubernetes and continuous delivery. Despite this, rebel spaceships striking from a hidden cluster have won their first victory against the evil galactic empire. During the battle, while the Jedi were busy studying the book of Istio CRDs, the Empire managed to capture Leia and bring her to the Death Star. So we're here in the movie. In this scene, Leia, no, Alderaan is peaceful. We have no weapons. You can't possibly. Then name the system. Where is the rebel base? Looks at Alderaan for a moment, then resigned. Dantooine, they're on Dantooine. So that's the setting for our demo. So I'm switching tabs here, and you will see I have my terminal split. And in the upper half is my cluster 1 running on GKE. On the lower half is cluster 2 running on EKS. And GKE is actually in Europe, and EKS is in the US. So I'm trying to make this as difficult as possible. So let's check whether we actually have connectivity to my cloud provider. Yes. Okay, it's a bit lagged, but so I have 3 nodes running in GKE, and I have 2 nodes running in EKS. I have a bunch of pods running here. So we have Rebel Base, and we have X-Wings. And in my EKS, I have 2 Rebel Bases. I also have a Kubernetes service Rebel Base. So let's look at this. For those wondering, K is just my short alias for kube control. So we have a Rebel-based service, and it has a cluster IP. And you can see that this cluster IP is different from the pod IP. So these are the pod IPs, right? Then we also have this endpoint structure that we discussed before. I can look at this, so we have a Rebel base, and you can see that this endpoint structure contains the 2 pod IPs, like this one, of the 2 Rebel-based pods, right? So Kubernetes is actually only aware of the local pods. Kubernetes does not know about the other cluster at all. As I saw when I did kube control get nodes, I did not see any additional nodes. So our global service routing does not actually connect the control plane of Kubernetes together. The Kubernetes clusters are still have exactly the same scope. So I can go into an X-Wing. I will do kubecontrol exec. I will just launch a bash. So I'm now piloting an X-Wing. It's pretty cool. And the X-Wing can curl the Rebel base, and the Rebel base will return and say, I'm in Galaxy Alderaan, and I'm on GKE. We can also curl the service name, and let's do this a couple of times. All of a sudden, the response was different, and somebody from Dantooine in EKS actually responded. So how did that work? Cilium transparently did load balancing and synchronized the services in our cluster 2 in EKS and made it available in the first cluster. and then does standard load balancing based on Kubernetes health check information. So if my pod dies or becomes unhealthy in cluster 2, it will be removed. So let's try that. Let's do a for loop. I'm really bad at typing. Let's do one more, so it just doesn't exit. So we'll just do this a bunch of times, and then we do curl rebel base. So we'll see that sometimes it returns GKE, sometimes it returns EKS, right? So what happens if we scale our deployment? So Kubernetes scale, that's how we can change the number of replicas. So we scale our rebel base. Let's scale it down to 0. Now it's only GKE. So this is very quick. So like we scaled it down, and now it's always going to the local cluster. I can scale it back up. You'll see that Kubernetes is now creating the containers, and as soon as the containers are up and the health check is responding, we see EKS coming back in. Nice, so we have load balancing now. What if I want to do policy, right? I still need to do security in all of this. So let's look at how security works. So I have a YAML file here that defines in this case, it's Cilium network policy, which is our CRD for policy, but this works with standard network policy as well. Look at this policy rule. This policy rule, it has a name, it says allow cross-cluster, has a description, allow X-Wing to rebel base within cluster 1. Description is actually wrong, it must be within 2 EKS 1. So this policy says it matches on all pods with the name X-Wing if that pod is in cluster 1, which is the GKE cluster. And then we allow egress to endpoints, two pods, which match the label EKS1, the cluster name, and the rebel base. So let's go out here and actually apply this policy. And I'll have a Cilium network policy loaded. I will need the IP address here. So we can go back into our X-Wing. And I should be able to do, let's see. So this is the IP of the pod in the other cluster, which is what we allowed. That still works. But if I try and do a curl to the IP in the local pod, that will not work. So all policy that Cilium and all policy that network policy allows will work in this model. And you can define policy to either include the cluster name, in which case you can define what clusters can talk to each other, or you can define a global policy and say, I want all my front ends to talk, all my back ends across all clusters. So it's a flexible model, and you saw we did not encode any IP addresses at all. The reason why this is working is because Cilium does identity-based enforcement and not IP-based enforcement, which does not require cluster 2 to be aware of the IP addresses in cluster 1 and vice versa. That's a benefit of the identity-based enforcement model. So let's talk a little bit about design principles. The first of all, and this is, I think, 80%, simplicity. Like, we wanted the usability of this to be as simple as possible. Right now, this is an annotation, but I think there will be interest in the community to actually standardize this in some form. We also wanted to avoid the need for a networking degree. So you don't need to understand subnets or routing. We'll talk a little bit about what you need to understand in terms of setting up VPCs and so on, but that's pretty simple. Also very important, it must be absolutely simple to troubleshoot and debug, right? You don't want to be in a position where this is not working and you have to wade through thousands of IP tables rules or figure out with TCP dump what's going on. So a design goal was also to make this simple. Then security. Obviously, like as we cross cloud providers, encryption is elemental. We want security policies spanning multiple clusters. We saw that in the demo. And we want compatibility with mutual TLS to run Istio or other service meshes. We want resiliency. We want to be able to not impact other clusters. If something is wrong in cluster 1, that should never have an impact in cluster 2. We do not want to actually run something globally that you have to manage and then all clusters connect to. So we preserve the failure domains, we preserve the availability zones, and make sure that clusters can live on their own, and Cilium does the connectivity on the networking layer. Efficiency, so we want this to be as efficient as possible, so we do not want to introduce additional termination, proxies, and so on, so we did not want to go across egress proxy, ingress proxies, and so on, so we wanted to use standard networking principles, which gives us the native performance. So we saw one annotation in the demo, which is global service true or false. We support a couple of additional ones. You can actually define whether a service should expose its endpoints to other clusters. So you can say, I have a service backend, but I don't want to expose my own pods to other clusters. I just want to use endpoints of other clusters. Coming soon will be service affinity. So you want to be able to define a policy and says, go to the local cluster first, and if there's no healthy backend, then go to the remote cluster. You want to do local node, right? Always prefer a backend on the local node, then go to a local cluster, then go to the remote node, and so on. Not implemented yet, but coming soon. If you want more, talk to us on Slack. Control plane. So actually, let me show you this. All is better. Right? So Cilium is running in a namespace called Cilium. And you will see that we're running Cilium itself. That's the agent that's running as a daemon set on all nodes. Then we have an operator which synchronizes Kubernetes services to an etcd. That etcd is actually managed by Cilium itself. So we have a Cilium etcd operator which then manages the etcd operator, and the etcd operator manages the etcd cluster. So Cilium comes kind of bundled in one namespace, deploys itself, and synchronizes the Kubernetes services that you have annotated into the etcd. We have then a service, which is called Cilium etc external. This is a type load balancer service with an annotation to make it VPC internal. So this is not exposed on the internet. This is exposed inside of your VPC. And it is protected by TLS. So the operator automatically creates secrets, and then we have scripts to extract the secrets, import them into another cluster to establish control plane connectivity. So this is not just free for open. You need to share, so in order for a cluster to be connected, cluster 1 needs to share the secrets to cluster 2 in order for cluster 2 to connect. So that's our security model. We will then have all agents in the other cluster connect to that remote etcd and watch for service changes. So whenever something changes, as new service is added or the list of endpoints is changing, the etcd key will change and the agents in the other clusters will receive a notification. It's important that all agents do this connectivity. It means that we don't have a single point of failure. So if there is a problem with one Cilium agent in one node, in one cluster, this will not have impact on other nodes. So we want to be as distributed as possible. I included the example here on how you can do the internal load balancer type on GKE. There's, I think, all cloud providers support this. I haven't checked, but at least Amazon and Microsoft support this as well. So let's look at the VPC or at the kind of setup on the infrastructure side. It's pretty simple. You create 2 VPCs, and you can create as many clusters in those VPCs, but you need 1 VPC on each side. The CIDR block, the IP range assigned to the VPC must be unique, so you cannot just use the same IP address. And that's requirement number 1. We could support overlapping IPs, but I think for simplicity, you actually want to have unique IP addresses anyway. You will then establish a VPN gateway. And so that's kind of a single click or a single API call. You then set up VPN tunnels. You want at least 2. You want redundancy. And then you set up routes to route the IPs of VPC 1 to VPC 2 across the VPN gateway. You can do static routing, you can run BGP, you can do whatever you want. Follow your cloud provider guide how to do this. All of the cloud providers have simple guides to follow. And everybody supports IPsec, so you have compatibility to cloud providers or even on-prem as well. You then set up Kubernetes, and you can set up Kubernetes in any way you want, self-managed, managed, whatever. I don't think we even need a specific Kubernetes version. I think even 1.9 would work fine. You deploy Cilium, and Cilium will deploy the daemon set. Cilium will set up etcd, will manage it. You will then extract the secret, which grants access to the other etcd, and deploy that into the other cluster. And that's it. At that point, you're ready to go. You can deploy pods, deployments, annotate them, and you will have global services. Use cases. So I already mentioned one, high availability, right? Running services across cloud providers or across clusters. And if backend is failing in cluster 1, it automatically fails over to cluster 2. But there are other use cases. One use case is shared services. You're probably running common services. And I'm using Vault here as an example, but Prometheus would be another one. DNS would be another one. Services that are needed by your other services, right? So by running Vault or something similar in a cluster, you can make it accessible from other clusters. And then you can just basically add more and more clusters as you go without having to deploy Vault in every cluster. So you can bundle your shared services in one cluster and manage it there. This may also have security benefits because whoever is managing or operating Vault does not actually need to have access to the other clusters, right? So you can do separation of concern and limit access. I think this is very interesting, very practical. So split stateful and stateless, right? You will have a bunch of stateless apps. If you limit the cluster to stateless only, that cluster can be thrown away, recreated very, very simply, right? You probably want to have, you will care much less about your stateless services, but for the shared or for the stateful stuff, Cassandra or other databases, you will need to put a lot of more thought into when you upgrade that cluster, when you move services, and so on. So splitting this will definitely simplify your operation. Another one, like CVE, right? So we all heard about the Kubernetes bug that was fixed quickly, bug in the API server. Basically, all versions of Kubernetes were affected. A lot of people thought, oh, we actually have to upgrade our Kubernetes cluster. We can't get away with just running an old Kubernetes version. So everybody was like, time to abandon the cluster. How does this help? Well, let's look at this simple version or simple example. You're running Kubernetes 1.9. It's actually affected by the CVE. You're running a front end, which is stateless, and you're running a data store. What if you could evacuate your stateless services to a newer cluster version, 1.13, use global services to still have the front end talk to the data store in the old cluster, right? You can just move this over. As we saw in the demo, like the handover is basically seamless. And then you can restrict access to your old cluster, to your 1.9 cluster, and you actually have time to upgrade that cluster or do whatever you need to do to fix it, and you can actually have your developers work on the newer cluster version. Istio integration. So we get this question asked a lot. So what is the difference, Envoy, Istio, Cilium, Kubernetes? So Istio primarily, and I'm simplifying this a lot, but Istio and Kubernetes are basically control planes, right? They do service management, identity provider integration, telemetry collection, a lot of other things. It's basically knows what to do, right? Knows what services to run, knows what deployments to run, and so on. Cilium, Envoy, data plane. Actually handling network packets, L7 requests, doing routing, load balancing, security policy enforcement, and so on. Data plane knows how to do it. Both Istio and Kubernetes right now have an idea of how to do service definition and management. So we have like Istio services and we have Kubernetes services. We chose to implement Kubernetes services first for simplicity, but we can implement Istio services as well. That's not exclusive at all. So Cilium is completely compatible with Istio and enhances it. To summarize, so Cilium, based on BPF technology, it comes in the form of a CNI networking plugin. We implement Kubernetes services, primarily replacing kube proxy there, and can bring advantages such as global services, better scalability, and so on. We implement network security, identity-based, very important for multi-cluster routing, DNS-aware, IP-aware, HTTP, REST, gRPC, and so on. Data protocol-aware, Kafka, Cassandra, Memcached, MySQL. We just added Go extensions to Envoy to extend Envoy with Go, and we're using this to add more and more data protocols. Like, it literally took us a week to add Cassandra support, so it's becoming very, very simple to make Envoy aware of additional data protocols, so we can do more finer-grained security, provide better visibility, and so on. And then, super interesting, we do sidecar acceleration. So if an application is talking to a sidecar proxy to Envoy locally, it's typically doing TCP. TCP is invented or built for like lossy network environments. If you're on a single node, it's always lossless. So what Cilium will do is it will see app talking to sidecar, socket to socket, take out TCP and just copy the data over the socket. It's about 3 to 4 times faster. The other element is SSL visibility. As your services talk to, let's say, cloud provider, data store services, database services, storage solutions, all of that data, all of that communication is SSL encrypted. Via a technology called KTLS, kernel TLS, we can split handshake and encryption and defer the encryption to after Envoy and provide Envoy and Istio and other service meshes with L7 visibility into communication that's leaving a cluster that is always encrypted. With that, I'm closing. I thank you very much for coming. If you want to learn more, we have a Slack channel which is very active. All of this is open source. That's our GitHub repo. We have good docs. You can follow us on Twitter to stay up to date. If you want to hear more about Cilium, there's another KubeCon talk in this room at 1:45, which will focus more on the security aspects. I think we have... Do we have time for questions? All right, we have time for questions. Yes, I will repeat the questions.
Okay. So there's a bunch of other Kubernetes stuff you might want sync, like, let's say, secrets.
Yes.
Beyond the secrets, coordinate clusters. What other Kubernetes, I guess, CRDs, does it sync and does it not sync?
So the question is, do we sync anything other than services right now, such as secrets? The answer is no, we don't. Would love to have a conversation on what makes sense. Definitely careful in just randomly syncing secrets, but definitely interesting concept. Definitely love to chat and follow up. Yes, over there. Okay. The question is, how does this relate to federation? You can use federation. This does not depend on federation at all. We are definitely interested to kind of evolve together with federation. We did not want to take on all of the complexity that federation brings. So right now it's completely separate but compatible. Yes? Okay, so the question is, can we do load balancing decisions on other elements such as health checks, such as latency, and so on? Right now, we do support weighted round robin, so you can say that certain backends should receive more traffic. We do not have latency tracking yet, but in the end, it's all implementable. BPF gives us the flexibility to do all of that, but right now it does not exist. Yes? The question is, can we replace Envoy? We don't even want to. I think Envoy is great. Cilium has Envoy filters on metadata, listener, network, and HTTP level. We heavily use Envoy, and we accelerate Envoy. So I think Envoy and Cilium are a great combination together. We can do, for example, faster L4 load balancing. So if you don't want to use Envoy for just L4, I think Cilium load balancing is a good fit. If you're talking about offloading HTTP, maybe, but there's no plan right now to fully do that. So I think Envoy and Cilium actually is a great combination to run. Yes?
With kubeproxy, accessibility to the IP table rules, those rules, it's very handy to be able to do that. Cilium is a BPF, what tools
The question is, if kubeproxy, you have IP tables rules, you can manage those, you can look at them, you can use TCP dump. So we provide tooling that is very similar, but we believe it's simpler because it's not rule-based, it's intent-based. So if you look at, for example, the policy, you will see the security identities that are allowed. You're not seeing IP addresses. You can still look at that, you can still use TCP dump. We think we actually provide better tooling. I don't have the time to demo all of that, but have a look, run it, and provide us feedback in case something is missing. Yes?
What is the performance penalty for encryption?
So what is the performance penalty of the encryption? It's using standard IPsec. There is clearly a performance penalty if you're encrypting. IPsec has the advantage that it actually uses accelerated CPU instructions if available, and modern CPUs do expose that and do allow for that. So this performance will be the same as if you use IPsec, right? It will make use of hardware if possible. I don't want to quote a specific number because it will really depend on what hardware you're running and whether you're running VM or bare metal and so on. Yes?
What about the case where you want to, maybe such as stateful applications across clusters where you want to speak to a specific pod versus a random service, a random pod behind a service?
Can you repeat it? I'm not 100% sure whether I understood it.
Sure. So if you wanted to, say, span an application across clusters, but you needed to address a specific pod, such as when you run stateful applications, so you don't want to go to a random pod behind a service, but you want to go to an exact pod.
Yes.
How would you do that here?
Okay, question, yeah, I think everybody heard the question. So first of all, Cilium is split. There is pod IP routing. You can talk to the pod IP directly in the other cluster. It will just work. So the global services, the load balancing, is split from the pod IP forwarding. You don't have to go through the service IP at all. You can talk directly to the other pod IP in the other cluster. But then you need service discovery that tells you what that IP is.
Thank you.
Yes? Question is, can you use Cilium with another CNI and just use the global services? Yes and no. We're just this close to publish our initial integration with Flannel to run on top of Flannel and KubeNet. So we basically leverage the forwarding decision of Flannel and KubeNet, and you do policy or load balancing, whatever you want with Cilium. We already run in combination with KubeRouter, so you can run Cilium in a mode where it just passes information on to KubeRouter. You can also run your own routing daemon, BGP daemon, and just tell Cilium to do direct routing, and it will route according to the Linux routing table. So yes, we want to split it. Right now, it only works for KubeRouter, Flannel, and KubeNet will be next. Yes?
How does DNS enter resolve? Are you using the port DNS or
The question is, how does the DNS resolution work? It's using standard kubeDNS. kubeDNS will return the service IP, and Cilium will do the load balancing from service IP to the endpoints, which means that in the Kubernetes cluster, the Kubernetes does not need to know about pod IPs in the other cluster, right? kubeDNS will return the service IP, the cluster IP. Yes? Sorry. Yes, go ahead. Yeah, yes. So actually I had 3 clusters connected, but I just wanted to keep the demo a bit simple. You can connect as many clusters as you want.
And another question, in your configuration use case, do you require the VPC to be already there for it to use, or if I already have it without VPC because I didn't know about it, and I still somehow...
The question is, do I need a VPC? We don't actually care whether you have a VPC or not. You need to be able to route traffic from nodes in cluster 1 to cluster 2. So the VM or whatever is running your node in the cluster 1 needs to be able to reach the node in cluster 2. Does that make sense? Yes. So this was a bit cloud provider specific, but as long as you satisfy node-to-node connectivity, it will work.
Okay.
Yes.
Since you're doing some fairly deep packet magic here under the hood, have you run across workloads or add-ons that get confused by this, or that this doesn't work well with, or you need to do specific workarounds, or is this just completely transparent to everything you've seen?
This is completely transparent. So this is on IP level, right? So it will work for UDP, TCP, SCDP, whatever. It works for IPv4 and IPv6. I think there are some specific applications that say Prometheus what actually looks at the endpoints resource of Kubernetes and talks directly to the pod IP. In that case, it would not see the pod IPs in your cluster. Is that clear? So like, on networking level, it's completely transparent, but not everything is actually using the Kubernetes service IP, how it's in the standard way.
The other thing I was wondering about specifically is anything that tries to verify the IP of what it's talking to and compare it with where it is. Have you run across any workloads like that get confused by this?
To be clear on this, when you say it's transparent as long as both ends are running Cilium, right? And you require both ends to be running
Yeah,
Cilium.
absolutely. So, well, you can totally define a service, define an endpoint structure, and put arbitrary IPs. The load balancing will work, right? If you want to have automatic service synchronization, then you need Cilium in both clusters.
Okay, we're out of time.
Thank you so much.